Yeah, you can start now.
Okay, so I'm going to share just a minute. I'm share my screen here. Fine. Okay. Get started. So you all can see my screen right now?
Yep.
Okay. Let's get started.
Go ahead.
Here. We're talking of 30 minutes or approximately.
Perfect.
Okay, so at first, Ramadan Kareem, everyone. Thanks for the introduction and the kind words. Today's presentation is titled Design Guidelines for Reinforced Concrete Three-Sided Culverts. And this work was conducted under the supervision of Professor Hisham Nagar of Western University. So in this presentation, I will start with the introduction, then the project description and field data, followed by the numerical models validation. Then I'll walk you quickly through the parametric study, which covers the effect of backfill height, installation method, soil type and compaction level, and as well as the complete compressive strength. The results of these design guidelines were used in order to come up with the developed design guidelines for three-sided culverts, as I will elaborate later, and I will end my presentation with some conclusions. So three-sided culverts were developed to provide large hydraulic capacity at sites with limited vertical clearance. Accordingly, they are produced in relatively large spans, reaching up to 16 meters of span, and low-rise profiles. From environmental point of view, three-sided culverts are more attractive compared to culverts with closed geometries like box culverts that we see here. And the reason for that is the water flows in its natural course, causing minimal influence to the marine environment. So for you who don't know about culverts, we have different shapes of culverts, one of which is the box culverts. Others are called bottomless culverts, which doesn't have a bottom slab here. They are called bottomless culverts. They have different shapes. The one we are focusing on right now is going to be the three-sided culverts with flat top slab. So if we have a look at the slab here, it's kind of a flat top slab. When speaking about buried structures like culverts, it's very important to introduce the soil arching phenomenon, which occurs due to the difference in stiffness properties between the buried structure and the surrounding soil mass. This results in increasing the stresses on the structure in case of passive arching and decreasing the stresses on the structure in the case of active arching. Accordingly, the free field stress or the applied earth pressure on buried structure is no longer the free field stress, gamma times H. Instead, a vertical arching factor is introduced in order to account for the soil arching effect. Of course, for the case of passive arching factor, the vertical arching factor is going to be higher than 1, and for active arching is going to be less than 1. Based on the intensive work on box culverts, we can find the design guidelines in different codes and standards. For example, the Canadian Highway Bridge Design Code, which does not distinguish between embankment and trench installations. Instead, it specifies 2 standard installations, namely B1 and B2 standard installations. The differences between B1 and B2 standard installations relate to the backfill soil type and compaction level in the side fill and bedding zones. The code categorizes the backfill soils into 3 different groups. We have sand and gravel, sandy silt, and silty clay. It specifies the required compaction level for B1 and B2 installations, of course, with higher compaction level for B1 installation compared to B2 installation for the same soil type. For each standard installation, the code stipulates a vertical arching factor and horizontal arching factors to estimate the lateral earth pressure on the sidewall of the culvert. We have minimum and maximum values for the horizontal arching factor. And the vertical arching factor is specified to be 1.2 for B1 installation and higher value of 1.35 for B2 installation. On the other hand, the ASH2 differentiates between embankment and trench installations, unlike the Canadian Highway Bridge Canadian Highway Bridge Design Code, and it specifies and provides different equations to estimate the vertical arching factor. For example, the first equation here is used to estimate the vertical arching factor for embankment installation. And in order to account for the compaction of the side fill material, the vertical arching factor is limited to 1.15 for compacted side fill and 1.4 for uncompacted side fill. The second equation here is for trench installation. And as you can see, the vertical arching factor for trench installation shall not exceed that of embankment installation, which indicates that embankment installation is more critical when it comes to comparing the two different installation methods. With the absence of studies on large span three-sided culverts, the current design practice is to design these structures following the same guidelines adopted for small span box culverts. So they use the design guidelines of, let's say, the small span box culverts to design the large span three-sided culverts. Studies on bottomless culverts are relatively scarce and limited to either arch culverts. So this is an example of an arch culvert, as I previously mentioned, or three-sided culverts with arched top slab. However, to our knowledge, that studies on three-sided culverts with flat top slab, which is the subject of this presentation and this study, did not exist by the time this research project was initiated. So now let's go to the project description and field data. So three different three-sided culverts, namely Remembrance, Pickering, and Oshawa culverts, were monitored during and after construction completion. The three culverts had a spans ranging between 7.3 and 13.5 meters. So we have 7.3, 10.4, and 13.5 meters. The backfill height was very comparable for the three culverts in the range between 3.1 and 3.8 meters. And we are referring here to the backfill height on top of the culvert. And when we're talking about the span, we're talking about this dimension here. The culverts were supported on strip footings with different geometries. So we have two with pedestals. So you see here a strip footing with a pedestal. And the Pickering culvert was supported on a strip footing without a pedestal. Moreover, each culvert represented a different installation method. So we have trench, zero projecting, and embankment installations. So the three monitored culverts covered a wide range of practical situations for three-sided culverts. It was planned to instrument the culverts with pressure cells and strain gauges. The sensors were distributed as shown in the following layout for Remembrance Culvert, for Pickering Culvert, and for Oshawa Culvert. Vibrating wire sensors were selected for instrumenting the culverts, and these pictures show the pressure cells and surface-mounted strain gauges that were used in this study, and this table actually summarizes the technical specifications of these sensors. The following pictures show an overview of the final instrumentation of the three culverts. And it's worth mentioning that Oshawa Culvert is the largest reinforced concrete culvert with flat top slab to be instrumented to date, with a clear span of 13.5 meters. So these figures display samples of the pressure cell measurements at different construction stages of Pickering Culvert. Stability of the pressure cell measurements at constant backfill heights can be observed, which gives us a kind of an indication of the stability of the readings. The following figures show the measured tensile and compressive strains at each cross section. And for time limitations, we will not go deeper into the analysis of the field data. However, it's important to mention that these field measurements were used to validate numerical models, as will be detailed in the following section. So we go directly to the numerical models validation, where the subsurface till soils were simulated using the conventional more material model, while the backfill soil was simulated using the hyperbolic Blankenstein material model. And it should be noted that all the culverts that were monitored were constructed following the Canadian Highway Bridge Design Code requirements for B1 standard installation. For the footing culvert connection, the precast units were first installed in the keyway on plastic shims, as shown in this picture. Once the unit was in place, plastic shims were added between the keyway and the sidewall to avoid any lateral movement of the precast unit. Sequentially, the keyway was filled with non-shrink wrap. And it should be noted that this connection condition is considered a hinged connection in the current design practice. So we developed 2D plane strain models for the 3 culverts, and this figure here shows an overview of the Remembrance Culvert model. The model width was extended 11 times the culvert span based on a conducted sensitivity analysis, of course, to eliminate the influence of any of the boundaries on the obtained results. The mesh and staged construction was considered in the numerical model. The mesh was refined within the zone of the culvert in order to ensure high accuracy within the studied area. Similar to previous numerical models addressing soil structure systems, an interface was defined between the soil and the culvert and the surrounding soil. What actually distinguished the developed models in the study is that an interface was defined to represent the sidewall footing connection that I previously described in the previous section or the previous slide, which was not previously considered in any study according to our knowledge. We developed linear elastic and non-linear models for the culverts. The only differences between the linear elastic model and the non-linear model is basically in the reinforced concrete material model that was used, as well as the simulation of steel reinforcement as shown here. So in the case of non-linear model, we use the smeared crack model, which actually accounts for the non-linearity of the material behavior of reinforced concrete as well as crack formation. And for this case, we have to simulate and represent the steel reinforcement appropriately. So for Pickering culvert, both the field measurements, which are the dots here, and the numerical model data, which are represented in the solid lines, showed non-uniform vertical earth pressure distribution on the top slab, parabolic distribution of the lateral earth pressure on the sidewall, and almost uniform contact pressure underneath the strip footing, with slight increase of the pressure at the footing edge near the water side. Similar earth pressures were calculated using both the linear and non-linear models, as you can see here, the green and blue lines. However, it was noted that the linear elastic model could not accurately simulate the structural performance. And by this, we are referring to the strain gauges, the strain measurements, as very high tensile strains were measured at the bottom surface of the midspan, right here, which was much higher than the values calculated using the linear elastic model. So the explanation is that the nonlinear model predicted the development of flexural cracks on the bottom surface of the top slab, as well as the outer surface of the sidewalls, as you can see here. This explains the measured high tensile strains at these locations, which is basically the formation of cracks. So the interior surface of the three-sided culvert was visually inspected in the field, and flexural cracks were observed on the bottom surface of the top slab, which agrees with the nonlinear model predictions. For Remembrance Culvert, field data were available at a backfill height of 1.7 meter by the time the models were developed. Thus, the numerical models were validated against the field data at 1.7 meter of backfill. The applied earth pressures were predicted at the final backfill height as well, which is 3.2 meter, and this was included, and the results were included in one of our publications. A year later, the final backfill height was reached, and the field data showed excellent agreement with the predicted values as demonstrated in the chart of the figures here. Similarly, good agreement between the measured and estimated pressures can be observed for Oshawa Culvert, the third one. And overall, this section illustrates how our confidence in the developed numerical models was built. In summary, both field data and validated numerical models indicate non-uniform vertical earth pressure distribution on the top slab, Moreover, the calculated average vertical washing factors ranged between 1.05 and 1.1, which is much lower than the 1.2 and 1.35 stipulated in the Canadian Highway Bridge Design Code for the standard installations. However, given that these results are limited to the 3 studied cases, we thought of expanding the work by developing an extensive parametric study to cover the effect of other influential parameters. So we'll go through the parametric study right now, where the validated nonlinear models of the 3 culverts were used in this parametric study. We developed a total of 62 finite element models to investigate the effect of the backfill height, the installation method, the backfill solid type, and compaction level. And for all these cases, the concrete compressive strength was 60 megapascal. Thus, a concrete compressive strength of 40 megapascal was used to investigate the effect of the concrete compressive strength. So let's talk about the effect of backfill height first, where we extended the backfill height on top of the culvert up to 12 meters. Looking at the load deflection curves, it can be observed that the load deflection continued almost linearly beyond the point of crack, which is the yellow stars here, until reaching the maximum backfill height at failure. Failure was manifested by a significant increase in the mid-span deflection, as denoted here, with minimal increase in the backfill height, which indicates ductile failure of the culvert. These figures show the deformed shape and crack pattern at failure of the 3 culverts, and it can be observed that for Remembrance and Pickering culverts with relatively high sidewalls, as shown here, the sidewalls showed bending deflection, so you can see bending of the sidewall here. However, for Oshawa culvert with relatively short sidewall, the sidewall rotated as a rigid body in the footing keyway. As for the location of failure, plastic hinges were predicted at the top corner of the sidewalls for Remembrance and Pickering culvert. However, the plastic hinge was observed at the mid-span of Oshawa culvert with the largest span, as I previously mentioned. The effects of the backfill height on the applied earth pressure represented these figures, where the results clearly demonstrated the increase of non-uniformity of the vertical earth pressure distribution on the top slab as the backfill height increases. And of course, the lateral earth pressure on the sidewall increased as the backfill height increased. This for Remembrance culvert, for Pickering culvert, and for Oshawa culvert, we observed that the increase was much more obvious due to the rotation of the sidewall in the due to the rotation of the sidewall, the short sidewall that there's a rigid body in the keyway footing, as previously discussed, where the rotation actually led to approaching the passive soil earth pressure condition. The effect of installation method was investigated by considering embankment and trench installations. Both cases, B1 and B2 standard installations, were simulated. The load deflection curves actually showed no influence of the installation method. Similarly, the installation method didn't show any influence on the lateral earth pressure on the sidewall, as demonstrated in this figure. The vertical washing factor was estimated at each backfill height, and it was observed that embankment installation, which is denoted in the triangles here, the triangle dots, actually the vertical washing factor showed that the embankment installation was more critical compared to the case of the trench installation, which is kind of in agreement with the ASH2 provisions. Thus, embankment installation was considered in the following investigations. So for all the coming investigations, only embankment installation was considered. For the effect of backfill soil type and compaction level, the three different soil groups defined in the Canadian code were considered. We have well-graded sand, silty sand, and silty clay. Different compaction levels were considered for each soil group, representing compacted soil like SW90, moderately compacted soil SW80, and dumped soil SW65. And please note that the number here reflects the compaction level. Different scenarios were considered by changing the compaction level of the side fill and backfill soils. The model notation was given by the compaction level of the side fill, followed by that of the backfill. For instance, here SW9080 represents the case of SW90 as the side fill material and SW80 as the backfill material. And as listed in this table, the considered scenarios represented B1 and B2 standard installations, the case of dumped soil, or the case where we do not compact the soil, and other cases like the case of compacted side fill and moderately compacted backfill. The load deflection curves showed ductile failure for the considered cases, where we can see that the case of compacted side fill and compacted backfill, which actually represents the case of B1 standard installation, yielded the highest capacities for all culverts, which is in green here, while the lowest capacities were calculated for the case of dumped soil, the black solid line here. Thus, this highlights the significance of soil compaction and soil confinement in improving the structural performance and capacity of three-sided culverts. And by this, we do not recommend to use dumped soils without compaction when constructing three-sided culverts. The vertical arching factor at each backfill height was estimated for the different scenarios as well. And the case of moderately compacted side fill and compacted backfill showed the highest vertical arching factors, which is the gray line here. Accordingly, such construction scenario is not recommended. On the other hand, the lowest vertical arching factors, which was very close to unity, or 1, as shown in the blue lines here, was estimated for the case of compacted side fill and moderately compacted backfill, which indicates that this might be kind of a favorable construction option in case high stiffness backfill material above the three-sided culvert is not required, like the case of light pedestrian traffic. Then the effect of concrete compressive strength. All the scenarios representing B1 and B2 standard installations were replicated while reducing the compressive strength from 60 megapascal to 40 megapascal. The load deflection curves clearly indicated the reduction of the culvert capacity as the concrete compressive strength was reduced. And this table here summarized the results, which indicated a reduction in the capacity between 22 and 36% as the concrete compressive strength decreased from 60 to 40 megapascal. Based on the results of the parametric study, we developed the design guidelines. So the estimated vertical arching factors for the scenarios representing B1 and B2 standard installations were compared with the values of the Canadian Highway Bridge Design Code, as well as the AASHTO equation, as shown here. The comparison indicated that the Canadian Highway Bridge Design Code values consistently exceeded the calculated values for all the considered scenarios. On the other hand, the AASHTO equation underestimated the vertical arching factor for some cases, as shown here. And it should be noted that the x-axis here is actually h over bc, where h is the backfill height on top of the culvert, and bc is kind of the outer width of the culvert, as shown in this schematic. Accordingly, the AASHTO equation was modified, and new equations are proposed for B1 and B2 installations in order to ensure safe estimates of the vertical arching factor for three-sided culverts within the considered range of h over bc from 0 to 1.25. Similarly, the horizontal arching factors were estimated and compared with the upper and lower bounds of the Canadian Highway Bridge Design Code, and this happened for B1 and B2 installations. The comparison indicated that the estimated values generally fell within the bounds stipulated by the code for box culverts, and therefore the code values were considered adequate for three-sided culverts as well. So for the horizontal arching factors, we can still use the same values stipulated for box culverts in the code. Regarding the service limit state, the Canadian Highway Bridge Design Code specifies limits on the crack width of non-pre-stressed reinforced concrete structures. The crack width is limited to either 0.25 millimeter or 0.35 millimeter, depending on the exposure type as listed in the table. The mid-span deflection, which is denoted as delta here, corresponding to the two maximum crack width, 0.25 and 0.35 millimeter, were determined for the cases representing B1 and B2 installations for both cases of complete compressive strength of 60 and 40 megapascal. These figures here show the calculated culvert span to deflection ratios. So span is S and the deflection is delta, so S over delta for all the analyzed cases. The data were statistically analyzed using the box whisker plot. And according to Savani et al. 2011, the mean plus standard deviation for a data set with no zero values represents the 84th percentile value. And as we can see, the data set we have has no zero value. Thus, the mean plus standard deviation was determined for each data set, as we can see here in the figures. And actually, values higher than the mean plus standard deviation were adopted for the design guidelines, which ensures that the proposed values exceed the 84th percentile. Accordingly, to satisfy the service limit state requirements, we are proposing that the mid-span deflection or the mid-span vertical deflection should be limited to span over 825 and span over 600 in order to ensure crack width limits of 0.25 and 0.35 millimeter respectively. Based on the presented results, the following conclusions can be drawn. So we have that reinforced concrete material nonlinearity should be considered for realistic prediction of the three-sided culvert deformation at ultimate limit state. These three-sided culverts exhibited ductile failure under the earth loading conditions. Embankment installation is more critical compared to trench installation in terms of vertical earth loads, which is in agreement with the AASHTO provisions. The mode of failure and failure location were not affected by the side fill compaction level. However, the deformed shape of the footing culvert system was significantly affected. The side fill should be compacted to at least the same compaction level of the backfill material of the same soil type. And in addition, very loose with the case of dumped soil without any compaction for the side fill and backfill soil should not be used in constructing three-sided culverts. Compacted side fill and moderately compacted backfill led to almost a constant vertical arching factor of 1 for all cases, as we previously discussed. And this may be a kind of a favorable construction option in case high stiffness backfill material above the three-sided culvert is not required. And we mentioned the example of light pedestrian traffic. The ultimate capacity of reinforced concrete culvert is governed by its concrete compressive strength, and we found that a reduction in the range between 22 and 36% was observed when reducing the concrete compressive strength from 60 to 40 megapascal. The vertical arching factors stipulated in the Canadian Highway Bridge Design Code for B1 and B2 standard installations consistently exceeded the calculated values for all the considered scenarios. On the other hand, the AASHTO equation underestimated the vertical arching factor for some cases. Thus, two equations are proposed to provide safe estimates of vertical arching factor for both standard installation for, of course, three-sided culverts within the range of H over BC between 0 and 1.25. The horizontal arching factor stipulated in the Canadian code for B1 and B2 standard installations for box culverts can be used for three-sided culverts as well. And finally, to satisfy the service limit state requirements, mid-span vertical deflection should be limited to span over 825 and span over 600 to ensure crack width limits of 0.25 and 0.35 millimeters respectively. These are the references as I used in this presentation. And at the end, I'd like to take this opportunity to acknowledge the organizations funding this project. I'd like also to thank the organizers of this event and hope it meets your expectations and you find it useful in a way or another. And many thanks for your attention. I think I'm just on time and would be pleased to answer your questions.